In this homework video guide, we will continue to develop our graphing skills, and for this very first question, we need to find all intervals on which the following functions are increasing or decreasing. So increasing just basically means when is the slope positive, and decreasing means when is the slope negative. Alright, so for this very first question, I have a polynomial function and it's graphed to my right. And if I want to find where the intervals are increasing or decreasing, I can do this algebraically by taking the derivative here. So that's going to be my very first step. So I will start off by writing y prime. So y prime equals, and if I start multiplying this out using the power rule, 2 times 3 is going to be 6. And that'll be 6x squared minus, and then 2 times 3 will be 6 again, so this will be 6x. And then the derivative of a negative 12 is just going to be, the derivative of negative 12x is going to be negative 12. Okay, so that's step number 1, and then we take the derivative and we set that equal to 0 to find the critical points. And I can see that I can factor out 6, which is my greatest common factor here, so this will be x squared minus x minus 2. And then I can put the 6 there, and then we can factor this. And then we need to find two numbers that multiply negative 2 and combine to negative 1. So if we do that, that's going to be x minus 2, and that's going to be x plus 1. All right, so that's looking pretty good here. If I solve for the quadratic here, I know that x would equal to 2 over here. And for this part right here, that would mean that x would equal to negative 1. So 2 and negative 1 are my critical points. After you have your critical points, what you need to do is you need to draw a number line here. So I'll do that right now. So here's my number line. I will put my two critical points on the number line. So my two critical points are negative 1 and positive 2. And over here on the right, I'm just going to rewrite my derivative here. So my derivative was f prime of x, and that equals to 6 bracket x minus 2 bracket x plus 1. And what we're going to do now to find the intervals where we're increasing or decreasing is that we're going to look at the three intervals that are given to us. So here's the first interval in yellow, here's the second interval in blue, and my last interval I will use yellow again. And what you want to do is you want to find numbers in those intervals and test them to see if the signs are positive or negative. If I look at this far interval over here, a very good test number that I can pick in this yellow region could be a number like 10, for example. And what we're going to do now is anytime we see an x here, we're going to replace those x's with a 10. So if I put a 10 here, that's going to be 10 minus 2, 10 plus 1, and then there's a 6 there, right? So what I see is that this is going to be positive, and that's positive, so that means this region is going to be positive. Okay. And then after that, I'm going to pick a number in the blue region, and I believe a very safe number that you can pick in this blue region is probably going to be 0. And if I plug in 0 back into my derivative function here, if I use 0, this will be a 0 minus 2 and 0 plus 1. And if I take a look at the signs now, this is going to be positive, negative, positive. And if I multiply all that out, that means the blue region will be negative, right? Okay, so a positive times a negative times a positive number gives you a negative result. Alright, so that's done with the blue region. And then now let's pick a number in the last region here. So maybe we can pick, I don't know, negative 5, for example. Alright, so if I test negative 5, I have 6 onto negative 5 minus 2 and negative 5 plus 1. And once again, I don't really care about the actual answer, I just care about the signs. So this will be positive, this will be negative, this will be negative. And if we multiply all those numbers out, a positive times a negative times a negative, that will give us a positive region over here. Okay, so in order to answer the question here, when are we increasing and decreasing? Well, we are increasing when x is less than negative 1 and when x is greater than 2, and we're decreasing between negative 1 and 2, so I can put the negative 1 here, the 2 there, I can put the x in the middle, and I'll put less than and less than signs. And that would answer the question there. Before I go on, I just want to go back to the graph here and just kind of explain the results through the graph here. So when you're doing problems, you're not given the graph here, but I will just highlight the answers right away just to kind of just ensure that we understand what's going on here. So if if I follow the graph down here, this is going to be negative 1. This is my other critical point, which is 2. And I believe our answer was plus, 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 and then negative, 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 and then another plus, 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 plus. All right, so once again, the question was where are the intervals where the functions are increasing and decreasing? Well, this right here, that blue region is a positive slope. Sorry, that green region, yep, and then the green part of this graph is also a positive slope, and if I go right down the middle here, that has a negative slope. So that's basically what we're looking for, is the regions or the intervals where the slope is increasing or decreasing. Okay, so once again, this is increasing, and the middle is going to be decreasing. Okay, let's move on to the next question here. All right, so my next question is h of x equals to x cubed times ln x, and there's my graph there that I will use to test at the very end. So if I want to find the intervals where we're increasing or decreasing, we can start by taking the derivative here. So h prime of x equals 2. Now I have a product of two functions, so we have to use the product rule here. So the derivative of x cubed is going to be 3x squared. Whoops. 3x squared, and then times that by ln x. And then I add that to x cubed, which is the first term, and then I times by the derivative of the second term, and the derivative of ln x is 1 over x. All right, so we're going to set this equal to 0 here. I guess we'll try our best to clean this up. I guess we have 3x squared times ln x plus, and then there's an x cubed and x, so that's going to be just plus x squared. And then from there, I guess I can factor out the greatest common factor, and the greatest common factor here now is going to be x squared, right? So we need to factor out the x squared. And if I factor out the x squared, I guess I have a 3 and a ln x, right? So that's going to be 3 times ln x. And then we have a plus. And then if I factor out the x squared here, I get a plus 1. And that's exactly what goes inside that bracket there. And then once we set this equal to 0 here, I take a look at the x squared there, and the only place where x squared is equal to 0 is when x equals to 0. And then if I take this expression right here, if I set that equal to 0, I basically have 3 ln x plus 1 equals to 0. If I solve for x, I can bring the 1 to the other side, that becomes negative 1. Divide both sides by 3, so I get negative 1/3. And then I can raise both sides to the power of e. If I do that, this will cancel off, and then I have x equals to e to the power negative 1/3. Okay, so e to the power negative 1/3, that's a weird one here. That's the same thing as 1 over e to the power of 1/3. And if you go to your calculator, this is roughly 0.7165. So that's a kind of an ugly number there, but feel free to use a scientific calculator to approximate the value there. Okay, after that, let's go ahead and draw our number line out here. Okay, so once again, we have our critical points right there, which is e to the power negative 1/3, and our other critical point was x equals to 0. So if I had to plot this, I have a 0 here, and I have e to the power negative 1/3 over here. Okay, and then once again, we're just going to test to see if things are going to work here. And let me start off by writing my derivative expression right here, which is f prime of x. And the derivative that I had was x squared bracket 3 ln x plus 1. All right, so now I have 3 regions, 1, 2, and 3. One thing that you would need to kind of consider as well is, although I have 3 regions, this last region right here, that region there actually does not exist. And before I start testing points here, one of the reasons why the graph does not exist when we're below 0 is because when we're looking at the ln function here, you can only take the ln of positive numbers, right? You can't take the ln of negative numbers, so right away I know the domain here is x is greater than 0. So when we're graphing this, basically the graph does not exist when x is less than 0. Okay, that's fine. Let's go ahead and pick a number in this blue region here. So maybe a number in the blue region is going to be maybe a 0.5. All right, so 0.5 is a good number that is in that region, because we've figured out on a calculator that e to the power negative 1/3 is 0.7165. All right, so if I go ahead and plug in 0.5 into the x values here, that's not going to be too bad. I guess this will be a positive number. But if I plug in 0.5 over there, we get a pretty small number there. So if you actually evaluate that with the calculator, it actually turns out that this part will be negative. So just go ahead and put that in the calculator. You just put 3 times ln of 0.5 plus 1, and we will get a negative expression there. So if I have a positive and if I times that by a negative, that just means this region is going to be negative. Okay. So for this question, it does help if you have a scientific calculator to kind of approximate the numbers here. Okay, and then a number in the yellow region here, over here, maybe we'll pick 10. All right, so that means this is positive, and this will definitely be positive. So positive times a positive is positive. Okay, so there you are. Okay, so if I had to kind of summarize the answers here, when are we increasing? We're increasing when x is greater than e to the power negative 1/3. And I guess we are decreasing when x is between, we're decreasing when x is between 0 and e to the power negative 1/3. And there's your answer like that. And if I had to go and just verify this on the graph here like we have over here, let me just kind of explain the answers one more time. So here's a horizontal number line right there, and basically let's just put the key values here, right? So this is 0, and we also have e to the power of 1/3 here, so sorry, e to the power negative 1/3. And that's probably going to be somewhere around here, I guess. That's e to the power negative 1/3. And as you can see, we have a positive slope over there, right? So that means this is going to be increasing. And over here, we have a negative slope over here. So the way we kind of illustrate that is with a negative sign there. Okay, so once again, this is the increasing region, and this is the decreasing region right there. Okay, so that concludes the answer for that problem, and we're going to look at a few more questions in this homework video guide. All right, here's the next homework question here, and I guess for these homework questions, we need to use the first derivative test to find all the relative extrema. So basically what we need to do is, essentially we need to find the max and min points. All right, so a little bit more work from what we were doing in the previous questions. In the previous questions, we were finding the intervals where the function was increasing or decreasing. But basically, we're going to do all that work again in order to find the max and min points. All right, so step number 1 is we're definitely going to have to take the derivative of this function one more time. And what you could do right from the get-go is you could rewrite this so that it's in derivative-ready form. So this will be y equals to ln x plus x to the power minus 1. And now we can take the derivative here. So the derivative of ln x will be 1 over x. And then the derivative of x to the power negative 1, well, that's going to be negative x to the power negative 2. And if we go ahead and simplify that, now we have 1 over x minus 1 over x squared. And our goal is that we want to set this equal to 0 and find the critical points. And I'm going to use the crisscross smiley face technique here. So if I do that and apply that correctly here, I would get x squared. And then this times this will be minus x, all divided by x times x squared is x cubed. Okay, and I guess we can continue to simplify this. So if I continue to simplify this, I can factor out an x on the numerator. So I get x minus 1 and x cubed there. And if I just take care of this part and this part right there, I know that this can cancel and that can cancel, and I'm left with just x squared on the denominator there. And now I can make this equal to 0. Okay, I guess when I look for the critical points now, critical points just basically mean when is the derivative equal to 0 or when is the derivative undefined. Now, when the derivative is equal to 0, I take my numerator here, and I set that equal to 0, so this gives me an answer of x equals to 1. And if I look at the denominator here, if x equals to 0 there, that will make my derivative value be equal to undefined. So my two critical points are x equals to 1 and x equals to 0. Perfect. Okay, and one thing we're going to do now is we're going to draw a number line here, and on that number line I'm going to place the value of 0 and 1. And one thing I'll say right now is this part of the graph does not exist, because we're dealing with a ln function, right? And the domain of a ln function is greater than 0. So we're looking at just two regions for this particular case here. We're looking at this region and that region. Okay, so what was my derivative expression again? Okay, well, my derivative expression was f prime of x, and once I simplified everything, I had x minus 1 over x squared. And once again, we just pick numbers in the regions and we plug those numbers into the derivative to figure out the sign. If I pick a number in this region over here, maybe I'll pick, I don't know, 100. All right, if I have 100 here, and if I plug 100 there and 100 here, I basically get a positive divided by a positive, so this region is going to be positive. Okay. And if I pick a number in this region here, maybe the safest number is 0.5. If I plug in 0.5, I get 0.5 minus 1 all over 0.5 squared. Well, clearly the denominator is going to be positive, but the numerator is going to be negative, so negative divided by positive means we have a negative region right here. Okay, so based on that, if we use the first derivative test now, when we go from a negative slope to a positive slope, this means we have a minimum right here. Okay, so there's a minimum at x equals to 1, and now we need to find out what is, we know that we have a minimum at x equals to 1, but what's the corresponding y value? Well, all we have to do now is we go back to the original problem here, and this is our function here, and we have to evaluate f of 1. So what is f of 1? Well, f of 1 is going to be ln of 1 plus 1 over 1. Ln of 1 is going to be 0 plus 1, and 0 plus 1 is 1. Alright, so here is my x value, there's my y value. So the way we finish off our question is that we say that we have a minimum at the points 1, 1. So this is a minimum here. And that's it. That would conclude the answer for that particular problem, because we're looking for the relative extrema points. Alright, so let's keep on going and figure out how to find a few more relative extrema points here. And there it is. So here's my graph here. So if I were to graph this particular problem here, this is the function y equals to ln x plus 1 over x. And there is my minimum relative value right there. And notice once again, the graph does not exist over here, right? Because the domain is x is greater than 0 there. Okay, let's move on to another problem. Right, so in order to find the extrema points for this particular problem, we should take the derivative by starting with the quotient rule here. So y prime equals, we take the derivative of the top, so the derivative of e to the x is e to the x times the bottom, which is x, minus the top, which is e to the x, times the derivative of the bottom, which is just 1, and then we divide this all by the bottom squared. Okay, so there is my derivative, and then in order to find the critical points, we take the derivative and set equal to 0. I see there's an e to the x here and an e to the x there, so I can factor out the e to the x. And if I factor out that correctly, there's an x here and a 1 there, so that's going to be x minus 1, right? X minus 1. So just remember this minus sign is that minus sign right there, and then we divide this by x squared. Okay, so not too bad, and in order to set this derivative equal to 0, we need to figure out what x values make the derivative expression equal to 0, but we also need to figure out which x values make the derivative undefined, right? Those are our critical points. So here's my denominator here. This might be the easiest one. If the denominator equals to 0, that makes this expression undefined, and that's exactly what we want to find a critical point, the x values that make the derivative undefined. So for sure, when the denominator is equal to 0, it's undefined. And then let's take a look at this whole thing right here, x minus 1. Okay, so if I take that and x minus 1, if I set that equal to 0, that means x equals to 1. Now, if x equals to 1, that would make the numerator equal to 0, and that would mean that the derivative is equal to 0, so x equals to 1 is another critical point. Okay, so those are my critical points, and what we're going to do now is I'm going to draw a number line here, and I'm going to go ahead and plug in 0 and 1 on that number line, and my derivative here, y prime, is equal to e to the power of x, bracket x minus 1, divided by x squared. Alright, so let's test the regions here. Here's my first region, here's my second region, and here's my third region. If I pick a number like, I don't know, 100 in that region there, clearly this will be positive, this would be positive, and the bottom would be positive, so this whole region will be positive. Okay. Alright, let's go ahead and take a look at the next region here. So in the middle region here, maybe we can put 0.5. Alright, so that would make e to the x, that would be positive. This would be negative, and the bottom here would be positive there, so this whole region should be negative. Okay. And then if we keep on rolling along here, let's pick a number over here, maybe negative 10. If I plug a negative 10 into this expression right here, this expression is actually always positive regardless of what you put in for the x value. So this will always be positive, this will be negative, and this expression here should be positive. So when we multiply all that out, we actually get a negative region over here as well, right? So we have a decreasing region in two parts there, right? Okay, so based on all the numbers there and basically once we tested everything, I guess we have a minimum at x equals to 1, right? So when x equals to 1, we have a minimum. All right, so how do we find the y value? Well, we take this x value here, our critical point, and we go back to the original problem here, and we evaluate f of 1. Well, what's f of 1? Well, that's e to the 1 divided by 1, which equals to e. So basically, we have a minimum at the point 1 comma e. Here is our minimum. Sorry, I'll say minimum value, min value. Okay, and just before we finish this off, here is a little graph of the original function here. So if you went to your graphing calculator and graph this is the function y equals to e to the x all over x. And this point right here is the point 1 comma e, which is our minimum point there. So that is the only extrema value in this problem. Okay, let's move on to another one here. I'll try to do this one a little bit faster here. So we need to find the relative extrema points. So it's a product here. So we need to start with the product rule. So y prime equals to bracket 2x times e to the power negative x plus x squared. And then the derivative of this second part is going to be e to the negative x times negative 1. Right, and then we take our derivative and we set that equal to 0. And then on the left-hand side, we just clean everything up. So this will be 2x times e to the negative x. And then if I take this negative sign and multiply that with that positive sign, I have a minus sign here. And I have e to the negative x times x squared. Okay. So that's looking pretty good there, and from here we need to factor out the greatest common factor. So I have e to the power negative x and e to the power negative x, so I can definitely factor that out, and I have 1x here and 2x's there, so my GCF is actually x e to the negative x. And if I factor out that correctly, from the first term, I guess the only thing that survives is going to be this 2 here, so this 2 will survive, so that'll be 2 minus, and then over here, there's still an x left, so I have 2 minus x. So then I can close that bracket like that. And once again, if you're not sure if you did this correctly or not, you can always take this part right here and just distribute that into the brackets, and you should get this line over here. And when I do that, it definitely works out, so I know that I factor out the GCF correctly there. Okay, so when is this equal to 0? Well, from this expression right here, I guess x would have to equal to 2 for that bracket to be equal to 0. This part right here, e to the power negative x, this never equals to 0. And then we have a single x there, so that would only equal to 0 when x is equal to 0. So here are my critical points right there. Okay, so the next step is we draw a number line. We put those critical points on the number line. Here's a 0, here's a 2. My derivative here is going to be x times e to the negative x onto 2 minus x. And I just want to say that this part right here, this exponential function here, this is always going to be positive regardless of what number you plug in for x. Whether you have a positive or negative number, it doesn't matter. That part is always going to be positive. Okay, here are my three regions. Let's start testing numbers here. Let's just try 100 again. If I try 100, then this will be positive. We said that that's going to be positive, and this will be negative, right? So if I multiply that out, this means this region is negative. Okay. Next part, let's try 1 from that region. So if I plug in 1 there, I get a positive. That's going to be a positive, and this will be a positive. So that means this region is increasing. And finally, let's pick a number over here, maybe -5. If I try -5, basically what happens is this part here will be a negative. That will be positive, and then I believe this will be positive as well, right? So, positive times a negative gives you a decreasing region over there. Okay, so there you go. We've tested all the numbers here, and I guess what we conclude now that we have a minimum here, and we have a maximum over there. Okay, so there's a minimum when x equals to 0, and there's a maximum when x equals to 2. And then one more thing we could do now is we can go back to the original problem here, and we can go ahead and evaluate those two values there. So f of 0 and f of 2, right? All right, so f of 0 isn't too bad because x squared, so 0 squared will be 0, so that's 0. So what that means is at 0, 0, we have a minimum. For f of 2, if I plug in 2 over there and there, I guess we get 4 times e to the power -2, which is 4 over e squared. Okay, so our next point is 2, 4 over e squared, and that right there is our max. Okay, let's move on, and let me give you a graph of the final, if I take a look at the graph here, this is the original function here. So if you were to graph this, this is y equals to x squared e to the -x. And this point right here is the point 2, 4 over e squared. So there's our max. And then we have a minimum right here. And our minimum point is 0, 0. All right, so those are the solutions to that particular problem, and those are the relative extrema points. All right, let's keep on going. I think we have one more to go here. All right, classic problem here where we have to use the quotient rule here. I would say the algebra on this takes a little bit of time, so I'll do my very best to do the algebra here. So let's go ahead and find y prime. Y prime using the quotient rule means we take the derivative of the top. So the derivative of the top is going to be -1. And then we multiply that by the bottom. Quotient rule says we have a minus sign, times by the top, and times by the derivative of the bottom, which is 2x. And then we divide the whole thing by the denominator all squared. And there you go. Okay, so for sure we're going to set the derivative equal to 0. And what we're going to do is we're just going to clean up the top here. So if I multiply that out, I get -x squared minus 5. Now the next part here, I'll try to do this this part here in green first. So if I actually multiply that out, we get a minus sign and then a bracket of, I guess that's what, 4x minus 2x squared. And, whoops, wrong bracket there. And if we distribute this minus sign now into the brackets, we get -4x plus 2x, right? So if I just erase this and this, we get -4x, and then this will be a plus 2x, right? And now if we start combining like terms, this term and this term, if I add that together, we get positive x squared. So we get positive x squared. And then if I combine this -5 and this -4x, well, actually, we can't really combine that. We just have -4x and -5. And then the bottom is going to be x squared plus 5 all to the power 2, and that equals to 0 there. Okay, so a little bit of work to kind of simplify that derivative expression there. So the quotient rule always requires a little bit of additional algebra to kind of get it derivative ready. And then from here, I would just maybe factor the numerator now. So we need our factoring skills here. All right, so this will be negative 5, and this will be plus 1. And then we divide that by x squared plus 5, all to the power 2 there. Okay, so in order for us to find the critical points, this happens when the derivative equals to 0 or when the derivative is undefined. Well, on the bottom here, this never equals to 0, so the derivative is never undefined. And if I take a look at this expression, this expression right there, I know that the critical points are x equals to 5 and x equals to negative 1. Okay, so from there, I guess we can create another number line here. And I can put the negative 1 there and a 5 there, and this is y prime equals 2. And let's go ahead and write x minus 5, bracket x plus 1, all divided by x squared plus 5, all to the power 2. Okay, so let's go ahead and find numbers in the regions here. So let's pick 100 again. So that means this will be positive, this will be positive. The bottom is always positive, so this whole region should be increasing. Okay, pretty good. Over here, let's pick another number here. Let's try 0. Okay, if I plug in 0, what happens here? I guess this will be negative, and this will be positive. And if I multiply all those signs out, we should have a decreasing region right there. And finally, over here, let's go ahead and plug in, I don't know, negative 5. If we do that, I guess this will be negative. This will be negative. So a negative times a positive is going to be positive. So this region is increasing. Okay, fantastic. All right, so I guess we can conclude that there's a max at x equals to 1, and we have a minimum at x equals to 5. So those are the results there, and now we need to find the the y coordinates here. So now let's go back to the top here, and let's go ahead and evaluate f of negative 1, and we evaluate f of 5. Okay. I guess if I plug in negative 1 there, we get 2 plus 1, and on the denominator we get 1 plus 5, which is 3 over 6. So when we have negative 1, I guess the y value would be 1/2, and that's our maximum point there. If I plug in 5 here, I guess I get 2 minus 5 all over 5 squared plus 5. This equals to what? Negative 3 over 30, I guess. And this equals to negative 1 over 10. Okay, so our other point here is 5 comma negative 1 over 10, and that right there is our minimum. Okay, almost done this homework video guide. It was definitely a long video here, but here are the results. So here is my relative max, and here's my relative min, and these are our points here, right? So this was 5 comma negative 1 over 10, and this point right there was negative 1 comma half. Good. All right, so that concludes this homework video guide.